Добрий вечір, малята, любі хлопчики та дівчата. Мій шлях фізику почався звідси. Я навчався в Київському, в Українському фізико-математичному ліцеї. Я дуже вдячний вчителям нашого ліцею. І я хотів подякувати організаторам за те, що за цю можливість розповісти про деякі з моїх досліджень. Alright, so currently I work at the University of Exeter. It's not a very famous university, but it consistently ranks among UK top 10. I have quite strong quantum systems and nanomaterials group, where we do graphene science. This place is in Devon. Devon is southwest of England. It's well described in the Hound of Baskervilles. One of our well-known achievements was the discovery of a new material called Exeter. It's a potential replacement for the material known as ITO, which is used in touch screens in many mobile phones and other electronic devices. So we have other research activities, and we have a PhD program. We have a center for doctoral training in metamaterials. So some of you might be interested in this. All right. So now about my talk about graphene. So some things which I'm going to say now will be rather banal for experts, but if you think it's simply banal, just be patient. So let me first explain what solid physics or condensed matter, as known now, is about. So mobile phone is a typical solid-state device. There is a lot of various solid-state effects in every mobile phone, and one might ask a simple philosophical question: what is mobile phone made of? And the answer depends upon whom you ask. So if you ask a high-energy physicist, they would tell you, well, it's made out of protons and electrons. Oh no, wait. Now we know it's made out of quarks and electrons. If you ask a string theorist, they say, no, it's made out of strings. And a solid-state physicist is someone who asks the question differently. A solid-state physicist would say that you can't see quarks because they are combined in protons. No one has seen strings so far. And in fact, you can see even protons and electrons if you just look at mobile phone. Effectively, if you look at many solids, they don't look like random collections of protons and electrons. Instead, effectively, they look like as if they were made of different kinds of particles, as if they are made of things called quasiparticles. And the properties of quasiparticles can be rather different from properties of protons and electrons. So for a solid-state physicist, quasiparticles, the effective particles which populate electron device, are more real than protons and electrons, or even smaller particles. For high-energy physicists, it's the other way around. So basically, the approach here is the famous duck principle. If you say something which looks like a duck, walks like a duck, swims like a duck, walks like a duck, if it behaves like a duck, then it is duck, whether it's a real duck or a duck made of plastic, or just some pixels on the screen of your mobile phone. If it behaves like a duck, then it is a duck. And quasiparticles in many solids are basically such plastic ducks. So More specifically, quasiparticles are often introduced as follows. You have a solid, a collection of electrons, protons, interacting via Coulomb forces. Quantum mechanically, the system would have some ground state. You could look at the excited states. So if you excite the system, that costs you some energy, and at least this would also involve transferring some mechanical momentum. Maybe it will involve transferring charge. Maybe this would involve transferring spins. So based on this, one can introduce excitations of solids called quasiparticles. So quasiparticles can be characterized by their energy, their momentum. One can think of them as de Broglie waves. So then the energy momentum dependence defines the dispersion of de Broglie waves, so you can find out the group velocity and all other standard things from the optics. Sometimes the dispersion simplifies. You can introduce the mass. So for example, if you have an electron in vacuum, you can think of this as a quasiparticle with energy mv squared, or condensed matter physicists normally would write this as p squared upon 2m. By the virtue of well-known relations. Quasiparticles could be characterized by their charge, their spin. As particles, one can think of them as bosons or fermions or something else. And you could have some internal quantum numbers. So quasiparticles aren't electrons. Often their properties can be significantly different from those of electrons. And this quote illustrates that scientists in Ukrainian Institute for Physics and Technology understood this very well in mid-30s. That quasiparticles are different from electrons. They could have an arbitrary relation between their energy and their momentum. It's not necessarily quadratic, and you should always remember about this. But the actual importance of the difference between particles and quasiparticles probably wasn't fully understood until recently, and maybe we still don't understand it fully. So, traditional solid-state physics was based on looking at electrons and maybe holes in metals and semiconductors. And often, if you want to describe electrons and holes in semiconductors, you can use the effective mass approximation. So you can just think that electrons are, the quasi-electrons are effectively electrons with the same charge, same spin. The only thing which is different is their mass. It could be much larger than the mass of electron, it could be much smaller than the mass of electron, but otherwise it's pretty much an electron. A very trivial example of quasiparticles is provided by superconductors. So you can think of superconductor as a collection of Cooper pairs. So electrons took the interactions grouped into pairs, and those pairs behave as bosons, not as original electrons. So the properties of quasiparticles in superconductor are very different from the properties of electrons. The charge is different, the statistics is different. There are other examples of quasiparticles, for example, excitons, electrons, and holes. And in the last 30 years, people start looking at more interesting type of quasiparticles. What happened was basically going from studying quasiparticles in real solids to looking at quasiparticles in artificial structures, such as two-dimensional quantum wells, where the motion of electrons is limited to only 2 dimensions, or quantum wires, where you limit the motion of electrons in 1 dimension. Effectively, that enhances the effects of interaction and results in new interesting correlated phases. One of them is fractional quantum Hall state, in which quasiparticles behave as particles with electric charge of 1/3. So it's not just a simple multiple of electron charge, the charge is fractionalized. These quasiparticles have unusual statistics. There are various speculations about how to use these unusual statistical properties for quantum computing. Unusual statistical properties means that the particles are neither fermions nor bosons. So in many quantum mechanics textbooks you can read that all particles must be fermions and bosons. There is a proof. Don't trust these people. This proof has a loophole, at least in 2 dimensions. A very similar thing happens in 1 dimension. There are, for example, carbon nanotubes on quantum wires, where again interaction leads to fractionalization of charge. You can have a charge and spin being split. So normally electrons would carry both charge and spin. Quasiparticles in interacting one-dimensional system carry either charge or spin, but not both. So there are many interesting effects. There's a whole new kind of artificial solids called atoms in optical traps. I'm not an expert in this, so I won't say much, except that today in optical traps you can simulate almost any imaginable solids. 10 years ago, a new material was discovered. It's called graphene, and that's a truly two-dimensional crystal. There are other similar systems, such as topological insulators. Later, the techniques used to fabricate graphene were modified to some other materials, such as molybdenum diselenide. And what's interesting for these systems is that electrons, or rather quasi-electrons in graphene and topological insulators are Dirac fermions. I'll explain later what that means. Briefly, it means that the charge is the same as the charge of electron, but dispersion law is different. The really interesting thing is that these quasiparticles have new internal quantum numbers. They have a quantum number called pseudospin, and they have a chirality. You can think of these internal quantum numbers as particles having several different quantized internal states. Very recently, there have been experiments on 2 new types of quasiparticles. People experimenting with superconducting junctions that have superconductor, normal system with spin-orbit, were able to observe some signatures of new type of quasiparticles called monolayer fermions. So these quasiparticles are fermions, but fermions which never move and which have somewhat unusual statistics. Very recently, people discovered a 3-dimensional version of graphene topological insulator. In this system, the quasiparticles are called biofermions. Significant fraction of what I'm going to say today is applicable to these materials, to topological insulators, but for simplicity I shall mostly concentrate on graphene. Graphene is the system in which interesting effects are used very clearly, and that's a system which can be investigated relatively easily. Alright, so what is graphene? Graphene is a new form of carbon. Carbon is a very interesting chemical element. It has 4 electrons in the outer shell, and these 4 electrons can form chemical bonds in several different ways. You can either use 4 electrons to form sp3 hybridized bonds, and then carbon atoms would form a very rigid, very solid structure called Dirac. Or instead, you can hybridize these states into sp2 hybridization, then you get 3 chemical bonds sticking out of each carbon atom, and you can organize carbon atoms into a 2-dimensional hexagonal lattice, like this. In real 3-dimensional material, such carbon planes are often organized into a stacked structure, and this stacked structure is known as graphite. Basically, the thing pencils are made of. When you take this plane of carbon atoms and wrap it into a tube, this thing is called a nanotube. If you take it and wrap it into a kind of bulky ball, then the structure is called fullerene. If you somehow take this plane out of graphite and isolate it, that's what is called graphene. So graphene is the thing is post-Bohr crystal, just 1 atom thick. You can't go thinner. Andrei Kaiman Kostonovsov invented a very clever and very simple way to fabricate graphene. Basically, they were peeling graphene flakes out of graphite crystals with a Scotch tape. They learned how to peel it off, how to transfer it to substrate, how to take the flakes via various clever experimental techniques, how to attach contacts, how to make electrical measurements, and do other interesting things. In the last 10 years, the field has expanded enormously. People came up with different methods of growth. Carbon vapor deposition, silicon carbide graphene, maybe some other forms which I don't even know of. People came up with different substrates. Originally, Andrei Kostonovsov simply placed graphene on silicon substrate, basically on glass. Now people can place flakes of graphene on much better substrates, which gives you lower impurity concentration, which gives you better transfer properties. So the quality of the samples improves drastically. Now graphene science is a huge field. Many people think are potential applications. So Andrei Kostonovsov received the prize for this 5 years ago. All right. So let me discuss what makes graphene interesting. For me, the most interesting thing about graphene is its electronic properties. The electronic properties come from a very simple fact. If you study the symmetry of hexagonal lattice, you find out that hexagonal lattice is based on unit cell made out of 2 atoms. Not just 1, out of 2 atoms. So as a consequence of this, the wave function in graphene has 2 components. One would characterize the probability of finding an electron on one of the blue sides, and the other would give you the probability amplitude for red sides. So the wave function has 2 components. In other words, the quasiparticle described by such wave function should have 2 internal states. So that is responsible for extra quantum number. Here, the spectrum of graphene is shown very schematically. So the most interesting feature of the spectrum is the existence of points called conic points. These points are placed in the corners of brilliant zone. So as you can see, there are 6 corners. They are pairwise equivalent. So one of them is called K, and the other is called K prime. And these are called values. So near each value, the spectrum is is conic, and near each value you can introduce two pseudospin states. So a very useful approximation for the electron spectrum near one of these conic points is this Hamiltonian. It's linear in momentum. It has a parameter called Fermi velocity or Dirac velocity. The relative spectrum of this Hamiltonian is linear, so we can be identified with the velocity of charge carriers. The significance of this equation is that it's very similar to the equation of dispersion for relativistic particles. These particles you have Cp. So if you try to identify this for relativistic particles, you have to conclude that the effective speed of light is Vf, and the numerical value is about 300 times smaller than the speed of light. So these particles are basically plastic ducks. I was talking from the very beginning. They behave like relativistic particles, yet they are made out of plastic. The actual velocity is 300 times smaller. All right. So if you go to one of Andrea Costa talks, they'll probably will give you a list of various wonderful properties of graphene. That it's super thin, super strong crystal. But for what I'm going to discuss is that it's conductive. So electrons near the Dirac point can be probed through electrical measurements. The surface of graphene is often open. You don't have to put any kind of substrate. You don't have to deposit anything on it, and therefore you can move around a tip of the scanning tunneling microscope or atomic force microscope, and you can literally probe every point of your sample. From a more theoretical point of view, it's important that the electron dispersion is unusual. So we shall talk about these aspects a little more. And one other thing is that in graphene you can adjust the position of the Fermi level. So in normal, traditional three-dimensional solids, you have to live with the Fermi level that nature provides for you, which comes out of the electron density. In graphene, you can move the position of Fermi level. So normally, undocked graphene would give you the position of Fermi level exactly at the conic point. But if you apply a gating to the sample, you could either move the Fermi level down and even more down, or you can move it up. So you can change between neutrality point, electron doping, and hole doping, and you can do it smoothly. So you can look how the properties change as you change the top, as you go from electrons to holes. Here is again the Hamiltonian which I tried to show you. Here is the linear dispersion. Let me say a few words about the quasiparticles. So the quasiparticles can be characterized by the two internal states. They can be characterized by their pseudospin, and this Hamiltonian basically tells you that the pseudospin must be aligned with the momentum of the particle. So here I try to show this schematically. So for this direction of momentum, electron would have pseudospin along the momentum, and pseudospin and the hole would have the pseudospin in the opposite direction. As you rotate the momentum, spin and pseudospin would follow this. So if you think about the spin of a particle, let's forget that it's a pseudospin. Again, we are talking. We are going to treat plastic duck as a real duck. If you think about the spin as real rotation, you said either the particle spins along this momentum, or it spins in the opposite direction. So in other words, the particle has a chiral. that's one important point. And another thing which should be mentioned is that with a spectrum like this, it's often instructive to characterize it by looking at the density of states. How many states are available for a particle at each particular energy. So for the linear dispersion, you can apply the standard equations from any statistical mechanics book, and here's what you get. The density of states is suppressed near the charge neutrality point and would increase away from this point. So here you have the band of electrons, here you have the band of the holes. They touch just at one point, just at one quantum state. So you can smoothly change electrons into holes almost at no energy expense, but there is a very small number of quantum states here, so quantum mechanics here becomes interesting. One interesting property of graphene is how the spectrum is reconstructed if you add more and more layers. For normal dimensional solids, you read in standard physics textbooks that if you have a conductor that thick, and then increase the thickness by a factor of 2, all that changes is that conductivity is now 2 times larger. Everything else is the same. For graphene, it's very different. If you add another layer on the top, if you add a red layer on the top of blue layer, the spectrum is reconstructed completely. So what happens is that the electron state here on the red side couples to the one on the blue side. They acquire large energy and go out of the game. So what remains in the game is the electron state here, 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 on the sides, which so the resulting band structure has this form. So you can notice that the thing that has changed is px minus ipy is now squared. So again, you have some alignment between the direction of pseudospin. Pseudospin has different mean. It's basically a top layer or bottom layer, and the momentum. So a similar diagram has this form. So pseudospin rotates twice as fast as the momentum. Since the energy is proportional to p squared, unsurprisingly, this portion is momentum squared. But one should notice that this matrix has 2 eigenvalues, positive and negative. That gives you 2 bands for electrons and holes. The density of states is completely flat. So there is no separation between electrons and holes. You can smoothly go from one band into another, and there is a large finite number of states when the 2 bands meet. So the thing which is common to single-layer graphene and bilayer graphene is the hierarchy of charge carriers. It works slightly different and somewhat similar to what happens for relativistic particles. And another thing is that there is no true gap between electron band and hole band. This difference can be probed in the experiment. So here are the measurements of Hall effect, the measurements of Hall coefficient of a sample in a strong perpendicular magnetic field. So you can notice that the curves for bilayer graphene and monolayer graphene are very different. The experts would recognize here have quantum Hall conductivity. So again, simply adding another layer completely changes the electronic properties of the material. And if you add in a third layer, the properties would change again. So now you can ask me some questions. So how do these particles move, and why is the pseudospin important? To explain why this is important, it's helpful to recall one thing for optics called Brewster's angle. So you know that if you shine unpolarized light on a reflecting surface and you properly select the incident angle, then the reflected light is fully polarized in one direction and unpolarized, and wrong polarization simply isn't reflected. So having particles with internal states, like horizontal vertical polarization, like a positive and negative chirality state, has an effect on transmission and reflection properties. In graphene, this works in a more remarkable way. There is a phenomenon called Klein paradox, first considered in condensed context by Kastner and Novisov and Guy. So they've looked at the standard quantum mechanical problem of transmission through a barrier. They have shown that if the particles are normally incident on the barrier, then they are perfectly transmitted. The transmission coefficient is 1. Nothing is reflected. So that happens precisely because particles have polarization. So when an electron is approaching a barrier, it enters the barrier in a certain chirality state, and to reflect it back would require flipping the chirality, and that just doesn't happen in this case. So that's what you get for monolayer graphene. For bilayer graphene, the chirality pattern is different, and the result is that you have a perfect reflection at normal incidence. Nothing is transmitted. Normally, in quantum mechanics, you learn that for nearly any reasonable barrier, transmission is different from one, and reflection is different from one. Sometimes the transmission is very small, sometimes reflection is very small, but they are never equal to 1 or 0 exactly. In this case, it does happen because of chirality of charge carriers. So that happens at normal instance. How this thing behave if we deviate away from the normal instance? There is a very interesting suggestion by Shytov, Falco, and Schuller that a p-n junction in graphene, a junction created by gating where electrons and hole meet, can be an example of a perfect lens. So the interface between electrons and holes would work as a material, as interface between materials with a negative refraction index. The reason it happens is the following. If you consider particles approaching the junction, a flat junction, then the momentum component along the junction is conserved. But for electrons and holes, the velocities are opposite, so the velocity direction is reversed, and so instead of normal refraction like this, you get a refraction with negative index like this. And so one can create a lens out of perfectly flat boundary. You don't need any curvature as is the case with conventional lenses. So geometric optics is perfect for this type of junction, so the lens should be aberration-free. Again, that's a consequence of the use of electrons and holes and the chirality of these charge carriers. One can ask, was it possible to observe Klein paradox directly? Was it possible to measure transmission equal to 1? Well, technically it's difficult because if you are doing electrical measurements, you probably apply some voltage here, you measure the current, and this current becomes angle unresolved. Electrons go through the junction at all possible angles, so you only get the integral of this picture. But in fact, it's possible to detect Klein tunneling if you apply magnetic field, if you curve electron trajectories, if you can control incidence angles at magnetic field, so then you can spot the point where the reflection coefficient is 0. So when reflection coefficient passes through 0, it changes the phase. And this phase affects quantum interference in this structure. So this way you can notice a shift in quantum interference pattern, and it was in fact possible to notice this phase shift in the real experiment, and that's one of the evidence for Klein paradox. All right. So let me mention the other thing, relativistic dynamics in graphene. You probably know from introductory relativity that particles cannot exceed the speed of light, that the correct formula for energy is this. Energy is augmented with this square root. Or if you write this in terms of energy-momentum relation, you get this square root of p squared plus m squared. For very small velocities, very small momentum, that becomes familiar p squared upon 2m, offset by the rest energy mc squared. For very high momentum, you approximate this as Cp, and that's what is normally called ultra-relativistic limit. In this limit, the particles always move with the speed of light, but their energy could change. So one can ask, what's the consequences of special relativity for quantum theory? The equation has been worked out by Dirac. Here is the famous Dirac equation. If you don't understand it, don't worry. The only fact which is important is that if you want to write Dirac equation in dimension 3, you have to assume that the wave function is a 4-component vector. So here you have 4x4 matrices. The wave function has 4 components, means that the particle has 4 internal states. The question was, of course, what are these states? You can identify twofold degeneracy with spin up and spin down. If you recall that electron is a spin for 1/2 particle, what's the origin of the other two states? Well, the origin is that if you actually solve the dispersion, you'll find out the relativistic root is plus minus sign. So the full dispersion described by this equation has 2 bands: positive dispersion, negative dispersion. In general, there is a nice gap between the two. These are electron states, and these states are either called positron states if you are a higher energy physicist, or Hall states, or valence band if you are a condensed matter physicist. So, if you are applying the small momentum and small energy, you only deal with these states. They never get mixed with the states in the positron band. So you get standard non-relativistic quantum mechanics. Things become interesting if you can somehow make these states interact. For example, if an electron from this state falls into the hole in this continuum, emitting photons. So that's known as electron-positron annihilation. There are other things. For example, you can try to take a level out of this electron continuum and try to pull it into the whole band. How do you pull a quantum level? Well, very simple. You have to apply an inductive potential, such as a Coulomb potential. So Dirac solved the problem for Coulomb potential for a relativistic particle, and he obtained that the energy levels would go way down to the unit gap. This solution was then refined, and finally, Gershkin, Zhidovich, and Popov considered what happens if the Coulomb potential is really strong. Really strong in this context means the charge of the nucleus in an atom exceeds 170. So they found out that a potential that strong would take an electron state out of this band, drag it through the gap until it enters the negative energy continuum, until it enters valence band or a continuum of positron states. After the state is dragged across, we would have electron level in positron continuum, so that will be particle exchange between the continuum and the level. This particle exchange would be seen as positron emission. So they concluded that the supercritical atom, the atom with very large nuclear charge, is unstable. So there is an interesting phenomenon. Unfortunately, you would expect that it should happen under very unrealistic conditions. The periodic table ends at 109 today. People tried to arrange an experiment to see this effect. For example, one can think that if you collide two uranium nuclei, each having charge of 92, then for a short instant of time, they would form a compound nucleus with the charge varying this critical value, so you see supercritical positive emission. But this experiment is hard. Its story is a separate drama. For now, suffice it to say that no convincing signature has been seen so far. In fact, this phenomenon is much easier to prove if you look at plastic duct rather than a real duct. If you look into the physics of electrons in graphene. So in graphene, the effective value of the speed of light is 300 times lower. And that brings the critical charge way down to quantities of the order of 1. So here is a paper by me, who is here, and Misha Kasnirson, who is one of the connectors to theory of graphene. We predicted the signature of supercritical behavior for charged impurities in graphene. And we worked out some consequences of the supercritical behavior. In condensed method, the experiments are set differently. We don't collide impurities. Instead, we place them in the sample. We have shown how the phenomenon occurs. Basically, the important thing is the following. In special relativity, there is a limit on the velocity of any object. Now, every physicist, I think, once in their lives at least solved the problem about a bucket which can be rotated upside down. If the velocity is sufficiently large, the water would be kept in orbit, it wouldn't fall down. But this doesn't work for a relativistic bucket because of the limitation on the velocity. So, under certain conditions, charged particle in a Coulomb field would descend onto the nucleus by a spiral trajectory like this one. At very short distances, where the field of the nucleus isn't exactly 1 upon r, the trajectory would be reversed, so it would be decompressed. So the quantum state in supercritical potential is breathing in and out, in and out, in and out. So there must be some kind of resonance. One can calculate the position of this resonance in energy. One can calculate its width and make some predictions for experiment. The story turned out to be sufficiently interesting that Mike Cromie, one of the leading figures in scaling time and microscopy community, got interested. So he and his students and postdocs performed a very nice experiment for which we provide the theoretical support. The idea basically was the following. You take graphene, you place calcium dimers on graphene, and Cromie and his team learned how to manipulate these dimers. So dimers have two charge states, on and off. You can bring it this STM tip, applies a pulse of solid string, and so you can switch it between the two states. So you can place dimers, and it looks like as if there are switches in them. So you can come and turn the impurity on and off, click, click, click. And so you can probe the behavior of electrons in the vicinity of such dimer by measuring the thermal density of states. So if you just take one dimer, the density of states isn't much different from the one without dimer. It changes with two dimers. Then, if you add three dimers, you can see that a peak is growing on this density of states. You put four dimers, the peak is higher and higher, and also moves in energy. So this peak can be identified with the atomic collapse state. So this peak is this resonance of the state breathing in and out. Okay, so that was the experiment. There were a few experimental anomalies though. The first was that anomalies show up if you start looking at the doping dependence of this thing. Let's start with deep hole dope. So then the Dirac point is here, and the atomic Coulomb peak is seen at the energy above the Dirac point. Well, the theory predicted that it should be always below this point, because basically it's electron level direct into the whole continuum. So it's slightly above, but never mind. Let's keep going. As we change the doping from deep hole doping to neutral to positive electron, you can notice that the peak loses intensity and eventually simply disappears. So one of your tasks here is to understand the doping dependence. I had the pleasure of supervising two smart master students. So they attempted to solve the problem numerically. We were starting with the impurity potential. We would calculate the wave functions from Dirac equation, calculate the induced charge density. This charge density would modify the potential. We would use this as an input to recalculate the wave function, and so on and so on, until the process converges. That's not a very sophisticated approximation, yet it yielded some interesting results. Here is the position of the resonance as a function of doping, and you can see that the resonance indeed starts with positive energies, goes deeper as you move the doping closer towards the charge neutrality point, then goes up in energy, and then suddenly disappears on the other side. The explanation for this basically is when the Fermi level is above the resonant level, you have 4 electrons sitting in the resonant state due to high degeneracy of graphene, due to value degeneracy, K prime, and the spin degeneracy. Self-consistent calculations confirm this simple picture. We also tried to investigate the resonance state at positive energies, and the explanation basically was that after you do the solid-consistent solution, that changes this form of the potential. The potential becomes screened, it's suppressed at large distances, and you can work out the detail of this. You can look at the trajectories in this potential. You can notice that these positive energy resonances come from trajectories like this. So here is this spiral describing true collapsing state, very sharp resonant peak, and here is semiclassical trajectory representing states in this peak in this broad peak at positive energies. So you can notice that this trajectory only makes one full turn, but otherwise it's not qualitatively different from this one. So that's a kind of precursor to the collapse. So it's not in the contradiction to the theory. There are other features. So to cut it short, self-constant theory describes the experimental anomalies on qualitative level, although qualitative agreement isn't perfect so far. Okay. I'd like to mention one project involving biolayer graphene. So one can ask what happens if you place a very strong impurity in a biolayer graphene? Will it create a resonance like this? Well, first you can start working on this by thinking what are the naive expectations. So here I have electron continuum, here I have hole continuum. If we try to put an impurity in graphene so that it would drag an electron state into the whole continuum, I will face the following problem. The density of states in the whole continuum is very high, so if there is any coupling between the states and the continuum, the state would dissolve into the continuum almost instantly. The only way out of this is that if the coupling is somehow suppressed. So here is my recent preprint in which I've showed demonstrated a mathematical miracle. So if you try to solve Schrödinger equation, then you can find certain decoupling. Again, you don't have to understand much here. The important thing is that the letter U only enters in the right equation, where there is no letter V, and letter V only enters the blue equation. So that's the equation for electrons, that equation for holes. They're completely decoupled, yet they could coexist at the same energy. I don't fully understand the origin of this miracle, but the implication is that this state in graphene is in fact an invisible state. So you have electron continuum, so you have a discrete electron level immersed into the whole continuum. Holes go around, they don't scatter into the state, they don't see if the state is occupied or not, for example. So in some sense, that's similar to the invisibility that Ulf was talking about. It's probably a kind of superposition of two solutions of invisibility problem. Here we have holes entering into the domain populated by the electron state, yet due to some peculiarity of refraction index, they just don't see the state. When I told this story to Lenya, he pointed out that a similar phenomenon, in fact, occurs in different geometries. For example, in flat barrier geometry. So again, under certain conditions, there is a decoupling between electron wave function and hole wave function, so they don't see each other. For circular geometry, I worked out some details when the phenomenon is best seen. So here is how one could potentially detect it. Create a cluster of impurities, say in the form of a ring or a quantum coral, and probe the density of states in the vicinity of the structure. So then the density of states would look like this. Very close to the ring, you'll see a very sharp, less than 1 millivolt wide peak in the density of states, and that would be this invisible state. All right. Computer is sort of unresponsive. I've just tried to show you the prediction for new kind of localized level in bilayer graphene. So far, there is no experimental support. Stay tuned, stay with us. So one of my PhD students was recently involved in a different kind of project involving localized state. So those were the states in single layer graphene formed by two quasiparticles in two opposite cones. The kinetic energies from the two cones would cancel, so one should look at small deviations from the cone structure. And the result was that a pair of electrons in opposite cones in graphene behaves as a particle with negative mass. So Coulomb interaction between electrons would effectively work. Repulsion between two negatively charged electrons would effectively work as an attraction. So there might be some kind of bound state. One thing which we don't fully understand is how to excite these states and how to detect them. Okay, so to conclude, one of the purposes of my talk was to convince you that the behavior of quasiparticles in graphene illustrates that quantum mechanics of quasiparticles can be much richer than mechanics of real particles. There are too many properties to be altered, and probably we still don't fully understand the consequences of changing to dispersion, introducing new quantum numbers, changing other things. So the field is ready. Get to work. Thank you.
Okay, let's return to a calcium atom on top. So does this mean that this position is a nucleus of this quasi-atom, yes?
Yes.
That you're talking about. But if you have 3 or 4 or even 5 calcium atoms, what would be this point?
Then basically it's the question about the size of the collapsing state and the size of the cluster. If the cluster is much wider than, if this the function of the state is much wider than the size of the cluster, it doesn't really matter. And that's the case in the experiment. So the cluster is about 1 nanometer in diameter, while the wave function extends to distances of 7 or 8 nanometers.
To how much?
7 or 8 or something like that.
Nanometers, yes. In this collapse state, yes.
Those
collapses, they are pretty large, yes.
That's what happens in this particular experiment. So if you change for example, if you had a 6 dimer, probably the wave function would shrink, and if you had more and more of them, at some point you'll have to worry about the structure of the cluster. But for clusters actually used in the experiment, the structure wasn't so much important. Although I agree, it's another interesting way to play this game. Move the atoms in the cluster, make it wider or narrow, and see what happens.
Okay, and then just a short second half of the question. Can you explain in simple terms why would there be an increase of the local density of states expected should this collapsed quasi-atomic state take place?
It happens because you have those collapsing orbits on classical. Then you have to quantize them. Say using the Bohr's overflow quantization rule, which says that an integer number of wavelength should fit into these states. And that basically gives you the collapsing peak.
Well, but is this because simply electrons would spend more time around? Because, yes, but in the scanning microscope you still have to see increased amount of electronic density at the end, yes?
Indeed, you can look at the energy and the width of the resonance, and the width of the resonance is roughly 1/7 of its energy. So it basically means that electron makes 7 motions in, out, and in, out before it leaves the state. So yes, that's time separation.
That's very easy. Thank you.
More questions, please? So,
yes, more.
If particles are constantly collapsing from this level to the sea of holes, where does energy of relaxation of electron which came to replenish goes to?
Okay, in the collapsing state, the energy is conserved. So you start at large distance from the impurity, you move closer in, momentum increases, kinetic energy increases, Coulomb energy also increases because of shorter distance, but the sum of the two remains the same.
Yes. You mentioned the experiment which observes this atomic collapse phenomenon.
Yeah.
Do you know experience by other group which observes the same phenomenon?
Yes. Unfortunately, for time restriction, I had to skip telling about all possible experiments. There were experiments by Eva and Ray, for example, where she looked at magnetic field dependence. So the thing is, if you have this collapsing state, the wave function becomes very sensitive to what happens at very short distances. Scale invariance disappears from this problem, and you can see this if you look at Landau levels near this impurity. So they are offset by Coulomb potential. In the subcritical state, there is a certain scaling between magnetic field and energy. In the supercritical state, the scaling is broken, but Lonia knows more than me about this because he interacted with this experimental team.
There was a slide where you said that these effects are due to some nearby effects, but why not something else?
Well, because of the doping dependence. So single particle physics should be basically insensitive to doping dependence. So you have the collapsing state, it doesn't care about where the Fermi level is, what all other electrons are doing. If the position of the Fermi level is important, if other electrons are important, that's the signature that this thing comes from many body effects. Does that answer your question?
Yes, so when you link your electron in physical, can you play with the thing tricks like Holmes talked about? Can you do something cool with it? Like heat?
Well, that depends on what the definition of cool. Well, for example, you can apply perpendicular field to the sample. This would introduce some mixing, so you can quench the state by the perpendicular field. You can quench it by magnetic field, which would change the angular momentum of the electron. Probably there are other possibilities, but I have to think about this thing.
So does it mean that if you shield it, you get longer spin lifetime or something like that?
Spin lifetime is an interesting question. Perhaps yes. For example, it would keep you can use it to keep the electron in impurity-free domain where the spin lifetime is larger for some reason. There is one problem with this state, which I didn't mention, which is that you can't have an impurity state like this. Because in bilayer graphene you have strong RPE screening. So I tried to calculate the critical impurity charge, it was something like 13. So you can't make this with a simple impurity, but you can make it with a cluster of impurities. Any more questions?
A question from a non-specialist. What are supposed main applications for
That depends upon whom to ask. Some people say that it's transparent, so you could attempt to use it for instead of ITO in mobile phones. Yeah, there are some projects based on this. So basically, you can't use it in direct form because the resistance is too high. So one of my friends in the department tried to heavily dope it with iron chloride to increase the conductivity to acceptable levels. Some people say that transport characteristics are very good. It's very small, so you can make transistors with small energy dissipation with very fast response rate. There is one problem. There is no gap between the conduction band and the valence band. That's okay for analog transistors, but very bad for digital applications. So there are several projects on how to introduce band gap in graphene to combat that. Some people say that it's so strong that you can, if you can make very, very big sheets of graphene, say meter by meter, you can have one atom support for your cathode. So projects are interesting. There are various proposals. History probably teaches us that there will be cool applications that no one expects at this time.
I also have a question about the end of there is some pair, Cooper pair-like state. So, are there any superconductivity observed in random
Unfortunately, no, because we spend some time trying to manipulate a version of supercompensate and such. The problem is that you can stabilize one player, but it's hard to stabilize the condensate of players.
So there is no superconductivity.
Instead, you might think about different things. For example, you could have a superconductor, graphene attached to it, superconductor would emit Cooper pairs into graphene by proximity effect, and then these Cooper pairs would have a large lifetime in graphene.
And can travel as a single.
But that's a scenario and not a theory.
Okay, thank you.
So maybe one last question. There are no more urgent questions, then let's send the speaker again.